Thank you. And I'd like to thank the organizer for giving me the opportunity to present our work. I've been at the KITP for 4 weeks so far and been very productive, and I'm very grateful. I wrote 2 papers, one of which was posted yesterday, appeared last night in California. This work is about the other papers that to appear. And my aspirational goal for this work was to derive useful swampland conditions from the first principle. And so I'd like to explain what I mean by that. So there have been many swampland conditions or speculation being proposed. And I think it's now time to roll up our sleeves and start proving or falsifying them. So that's one of my aspirations. And the other is to be useful. And so actually a few weeks ago, we had a discussion session at the KITP. And there, I think we had a diverse group, a variety of theorists came to have a panelist. They all agreed that there are some non-trivial constraints on low energy effective theory by consistency of unification of general relativity and quantum mechanics. But of course, people differ in the opinion of how useful such constraints are. So here I would like to define usefulness in the narrow sense, that it gives you a sharp constraint on low energy effective Lagrangian. Now, whether such a constraint is useful for particle physics or cosmology is the other question. But I think putting constraint on low energy effective Lagrangian is a prerequisite to such work. So that's my aspirational goal. So as I said, it has become increasingly clear, and I think we all agree that there are non-trivial constraints on low energy limits of quantum gravity that cannot be captured by the standard Wilsonian paradigm of low energy effective theory. And swampland is the idea to delineate between a landscape and swampland, to determine the boundary between them. So when we say derive, of course, we need to understand the ultraviolet compression. And AdS3 is one of the places where we can actually hope to have derivation from the fundamental principle. And so that's what I would like to do today. So in AdS, we can formulate and aim to prove or falsify such constraint in the language of CFT. And so for example, Daniel Harlow and I, like 5 years ago, proved that, that any global symmetry in quantum gravity theory in AdS would lead to an inconsistency in dual CFT. So this is sort of example of deriving a swampland condition from the first principle. But unfortunately, we cannot say that this was a useful constraint because, for example, the global symmetry in low energy effective action can be accidental and can be broken by arbitrary high order in the derivative expansion. So it doesn't give you a sharp constraint on low energy effective Lagrangian. So we want to be useful. So the distance conjecture can potentially be useful. It was proposed by me and Kumran 18 years ago. And there are several conjectures. I listed 3 of them. The first conjecture says that every parameter in quantum gravity is an expectation value of dynamical field, and therefore can be varied by changing an expectation value. That's a 0th order conjecture. And the first conjecture is that there is always an infinite distance in this moduli space. That is that if you choose any point in the moduli space in the bulk theory, then for any positive real number t, you can find another point which is distance greater than t. And then the second conjecture is to make it quantitative, which is to say that if you have such a distant point, then the mass decay, there is always a light particle with mass decaying at the exponential of e to the minus alpha t for some alpha. Okay, so these are 3 conjectures. So ever since we made this conjecture 18 years ago, I have been wanting to put some numerical constraints on alpha, because in order for this conjecture to be useful, we need to have a lower bound on alpha. Because otherwise, we can come up with low energy effective theory, which can avoid these conjectures, saying that, well, alpha can be much smaller than this, for example. So it would be useful if we can put constraint on alpha. Okay, now, so another aspiration is to derive such constraint. And in that department, there is a very nice work by Eric Perlmutter, Leonardo Asteri, Cameron Buffer, and Irene Valenzuela a few years ago, where they formulated this distance conjecture in the language of dual CFT, if you consider it in AdS CFT. So I listed two of their conjectures. They had 3 or 4 conjectures, but this is 2 of them. So one is that by using the correspondence between moduli space of AdS gravity and conformal manifold of CFT, which is a moduli space of conformal field theory, they conjecture that all points with higher spin symmetries are at infinite distance, and all CFT at infinite distance in moduli space have higher spin symmetry. Okay? So these are the 2 conjectures. The first conjecture was easier to prove, and in fact, in the original paper, they have already proven this for supersymmetric theories. And last summer, Baum and Calderon Infante showed that the conjecture 1 is true for any unitary CFT. So I heard this work at the Swampland meeting in Madrid last fall, and I thought, well, this is something I should work on. So I'd like to present the result of this investigation. I would like to point out in their work, so far there's no general constraint on alpha. So my aim was to find some constraint on alpha. And so we did that. I did that with EFAN 1 in the context of AdS3 and CFT2. So this is the work that I would like to present to you today. So this is a work in collaboration with EFAN 1, and I hope it will appear very shortly. So today I would like to explain to you these 3 statements. And hopefully this is, well, I cannot claim this as proof at the rigor of mathematics, but I hope it will be at the level agreeable to the theoretical physicist. So there are 3 statements I would like to present. One is that if there is a geodesic on conformal manifold along which lowest positive conformal dimension, which you may call as a gap in conformal dimension above vacuum, decays monotonically and vanishes at some point, then the homological distance measured by this conformal field theory calculation to that limit is infinite. The second theorem is that in that limit, the conformal dimension vanishes exponentially, like this. And so this was what conjectured by Kumran and me 18 years ago. But in this case, actually, we can prove that there is this exponential decay, and moreover, we can give an upper bound on this coefficient alpha. So this is, so I'm going to explain these 2 theorems first. And then, in fact, moreover, we can identify the necessary and sufficient condition when this upper bound gets saturated. Now, how about the lower bound? Well, so there comes the theorem 3, which is that actually we can know more about conformal field theory in that limit, which is that in the CFT at the limit is actually a direct product of sigma model in the decompactification limit. Namely, you can imagine n-dimensional torus, and the radius of the torus grows large, and then become Rn, for example, times some compact conformal field theory. And from this description, it follows that alpha is lower bounded by 1 over square root of C, where C is the central charge of the original conformal field theory. So it gives you a lower bound. Okay, so there are lots of words on this transparency. So I actually try to make this. Let's see, where is my pointer? Here. So there are lots of words here. So I try to make this more concise. So basically what I'm going to tell you is that this conformal dimension gap above the vacuum, vanishes only at the infinite distance in conformal manifold. And there it decays exponentially in the homological distance. And we can bound this coefficient alpha between 1 over square root of C and 1. So this is what I would like to explain to you. We make 2 assumptions. One is that we are assuming that this deformation is generated by exactly marginal operator. So therefore, in particular, we assume that this deformation does not change the central charge. there is an interesting question of what happens when you consider sequence of conformal field theory like minimum model, where central charge goes to some particular limit. And so it's not under the purview of this theorem. We might be able to extend some of the statement in such a case, but today I'm not going to talk about it. The other is that in order to prove this such a theorem, we need to know a little bit about what happens in the infinite distance. So we assume that the 4-point correlation function of a light operator whose conformal dimension becomes light is going to be well defined in the limit, doesn't diverge or anything. Yeah, Xiaohen. We can discuss that when I get to derivation, so then you can see where there is a possibility of orbit. It can also have a boundary in target space, for example. But we can discuss that after I present it, okay? Any other question? Yes?
Do you have any result in the converse direction if you just assume you have an infinite distance point?
That's my another future aspiration. Thank you. I'll come to that in my last slide. Any other question? Yes? No, I'm going to prove this for any unitary conformal field theory in 2 dimensions with discrete spectrum. Okay? Any other question before I get started? Okay, so let me get started. Okay, so this is a plan of my talk. So I'll first discuss example because examples are useful. And I prove the first 2 theorems. And I prove the last theorem. And I'll discuss the future direction. Okay, so that's my plan. Okay, so examples. The first example is a sigma model with target space tori. This is a very simple example, so this is the easy one. So the moduli space are parameterized by 2 complex parameters, scalar moduli and the complex moduli, and you have this Zamolodchikov metric. So there are various interesting points. For example, you can have orbifold point where you have some enhanced SU3 symmetries. And this is at a finite distance. It's a singularity of moduli space, but it's a finite distance. And in fact, there is a finite gap that doesn't decay. Now, the large volume limit is at infinite distance, and in fact, the gap decays exponentially. And this is actually one of the motivations of my original work with Cameron. And in that case, alpha hits the upper bound. Okay, so this is an easy example. The second example is more interesting. So let's consider the n equal to 2 superconformal sigma model with target space as quintic Calabi-Yau manifold. So this model has a variety of singularities. There is a Z5 orbifold fixed point, which is actually Gepner point. So you have superconformal minimum model tensored 5 times and the orbifoldized. And this has a gap. And this is actually a finite distance. And this is a gap. And we know what kind of field saturates this bound. This is a non-PPS primary operator with 0 R charge. So this is the orbifold theory. There is a conifold. Conifold is a very interesting point, and it's again a finite distance singularity in the moduli space. And it's also interesting because there is a continuum coming down at the conifold point, but continuum stops at 1/2, doesn't go all the way to 0. And this continuum is described by this SL2R Kazama-Suzuki type model. And so this is a finite distance example. And then there is an infinite distance point. So if you are careful and normalizing the Zamolodchikov metric, you find that there is actually 6 in front compared to 1 over here. So this one actually translates into alpha equal 1. So since this is normalized with 6, so alpha in this case is 1 over square root of 6, which is less than 1. So this is interesting. And I'm going to explain why this does not saturate the bound. This has to do with the existence of marginal operator near this infinite distance point, which are not exactly marginal. Okay, so these are examples. Okay, there is actually non-unitary CFT, which also exhibits interesting things. So this is a trivial example of non-unitary CFT. Let's just consider the same sigma model, this quintic sigma model, but just tensor it with the nonlinear, the non-unitary theory, with C equal minus 21 over 4. So this theory is non-unitary, and in fact, there is an operator of conformal dimension minus 1/2. Okay, but this has a normalizable vacuum. normalizable operator 1. So in this case, the conformal manifold of the theory is the same as the conformal manifold of this quintic sigma model. And this point contains a point where conformal dimension vanishes, because this has a continuum, as I said, goes all the way to 1/2 at the conifold point. And this has a conformal operator of conformal dimension minus 1/2. So if you combine them, you get the gap which vanishes there. But it's a finite distance. So you say that, well, this is a counterexample to our theorem. But this is counterexample because this is the non-unitary theory. So you see that in order to prove this theorem, we have to use unitarity. Okay? So these are the 3 examples that I wanted to mention. Shahan.
For non-unitary theory, we define the gap as the gap of 0.
I interpret my theorem as written. Okay, so now I'd like to present the proof of these 2 statements. I'd like to remind you of these proofs and the theorems. So namely, the first statement I would like to show is that it takes an infinite distance to reach the limit on conformal manifold where the lowest positive conformal dimension vanishes. And the second dimension, the statement is that it decays exponentially. That the conformal gap decays exponentially with the universal upper bound of alpha bounded above by 1. We also identify the necessary and sufficient condition when this bound is saturated. Okay? Okay, so let me first prove this theorem when there is only one exactly marginal operator and when this is exact. Okay? So this when it is exact. So that in this case, conformal manifold is 1-dimensional. In this case, actually, we show that the alpha saturates a bound at alpha equal 1. Okay, so let me prove it in the following way. So suppose there is a primary field O, whose conformal dimension vanishes at some point on the conformal manifold. So this is an assumption of the theorem. We want to prove that distance to that point is infinite. So choose a geodetic coordinate so that this conformal dimension delta of t monotonically decreases towards that point. Then there is a renormalization group equation, which basically says that the derivative of this conformal dimension along this geodetic is given by 3-point function of this operator with the exactly marginal operator m. This is this m. Okay? And the question is whether the distance t diverges. But if you look at this equation, you can easily say that t can diverge towards that point where delta vanishes, if and only if, only if this 3-point function vanishes at least linearly in delta. So now I'm going to show you a stronger statement that says that this actually vanishes linearly but with coefficient 1. So this means that by integrating this equation, this delta gap goes to the exponential of minus t, therefore alpha equal 1. Okay, so this is what I'm going to prove. Okay, so next 2 slides are the proof of this statement. Okay, so let me start with the following simple observation. We have this global SL2R symmetry, the conformal symmetry, so which we can use to show that if I take derivative of this operator whose conformal dimension becomes small, if I take derivative, there must be an operator j of this dimension multiplied by square root of delta. This follows from this conformal algebra. So therefore, you can prove that, you can show that 3-point function of jj bar m is equal to the 3-point function of this by this relation with the extra delta in front. So therefore, what we wanted to show was that this 3-point function goes like delta with coefficient 1, which is equivalent to say that the 3-point function of jj bar m goes to 1 in the limit. This is what I want to show. Okay? So to show that, I'm going to use conformal bootstrap, in particular crossing symmetry of the 4-point function of this operator O, which becomes light in the limit. So I'm going to expand this 4-point amplitude in terms of global conformal blocks. And global conformal blocks are nice because it's expressed in terms of our familiar friend, the hypergeometric function. Okay? And I was extremely happy when I remembered that F21 of 112 is equal to minus 1 over zeta times log of 1 minus zeta. Because if we use this fact, then we can actually write this crossing symmetry equation in this way. That because of this simple form, the crossing symmetry equation becomes of this form. And on the left-hand side, you have absolute value of Cjj bar square minus 1 divided by this function. And on the right-hand side is a function which is actually linearly independent of this function. So from this, it immediately follows that to the order of delta, this 3-point function has to be equal to 1. So therefore, you can show that this 3-point function of OM goes like delta, and therefore this follows. So this is a proof of this statement. Okay, so now suppose there are several, you have questions.
Is the right-hand side here an infinite sum?
This is an infinite sum, but I can show that continuum does not contribute from theorem 3, which can be proven independently. The right-hand side is infinite sum, but all these functions are linearly independent of this. Because all the hypergeometric functions are linearly, all the global conformal blocks are linearly independent in this case. Yes?
I think that J is a global primary.
It's become global chromatic in the limit. Yes, but you can think of this as a functional equation. Once you write this equation, then we can forget about all these quantum field theory statements. I'm just talking about functional analysis at this point. Yes? I have no idea how we prove it in higher dimension. But I think the original proof of Baum and Calderon-Infante has similar flavor to this. But they didn't use crossing equation. I think that one might consider doing this. So we are actually trying to do something like that, strengthening their result, and we might be able to determine, put constraint on alpha, but that's a work in progress. In high dimension, it's much more complicated because we have to worry about spins. Okay? Any other question? Okay, so far I have considered the case with when you have only one marginal operator and when it is exact. But in general, the conformal field theory can contain several marginal operators, and some of them may not be exactly marginal. In that case, by just trivial extension of what I just did, we can show that this contraction of this 3-point function with the homological metric goes to 1 in that limit. But some of these indices here, Mi, may go in the direction of not exactly marginal operator. So let's choose the direction where it is exactly marginal as Ma. And let's take the limit of 3-point function as alpha A. So then you can show that the norm of this vector alpha is less than or equal to 1. And it is equal to 1 if and only if the 3-point function to the marginal but not exactly marginal operator vanishes. Okay? And then gap decays exponentially like that. So if you choose the direction of, so that it goes in the direction of steepest descent, then it decays like so you can always write it in this way, and alpha is bounded by 1, and alpha hits 1, the upper bound, under the two conditions. First condition is that the 3-point function to marginal but not exactly marginal operator vanishes. And the second is that you choose the direction of steepest descent. And if you choose these two conditions, then you can have alpha hitting the upper bound. Okay? And otherwise it's less than 1. So that's the result of theorem 2. So this is a proof of theorem 1 and 2. Any question? Yes?
Can you explain the notion of linear independence for infinite set functions? You use linear independence for an infinite sum.
Yeah, but we have infinite sum of hypergeometric functions. And I think hypergeometric function has a standard linear independence properties. Well, so I'm talking about linear independence of this type of functions. So I'm saying that we cannot write this type of function in terms that can appear over here. That's my statement. You're asking me to clarify why this is the case? Okay, okay. Well, we can discuss that, but I think that we can talk about the terms that appear over here. Okay, any other question?
Could you clarify again what's the difference between O and J?
O and J are related by this equation. Is it okay?
Why did you just call it derivative of O?
We could do that too. It is just a simplified notation because then you have to write J is equal to 1 over square root of 1 over I times square root of delta times del of phi. And so this is just to simplify it, I wrote it as J. Any other question? Okay. So now I go on to the derivation of the third theorem, which says that CFT in this infinite distance limit is a direct product of sigma model at large radius and compact conformal field theory. And from this, it follows that alpha is now bounded below by 1 over square root of C. Okay. So in general, there are actually large number of primary fields. In fact, we will see that there are infinitely many primary fields whose conformal weight vanishes toward the infinite distance limit. And for each one of them, you can define this J. J's are linearly independent operators for finite distance, but they may become degenerate. They may become linearly dependent in the limit. So it'd be interesting to understand the relation. And we can actually find the relation between these operators by using operator product expansion of these right operators. So if you consider operator product expansion like that, we can write it in this way, where there are operator product expansion into right operator, and there are operators that we can also have contribution of. So in general, the spectrum can have the following structure that you can have operator whose conformal dimension becomes small and hits the ground, it's a vacuum conformal dimension. But there might also be some operators whose conformal dimension remains finite in the limit. So we can introduce some kind of parameter delta finite, which is sort of gap to this operator with finite dimension, who remains finite dimension, and all other operator goes to 0 dimension. Okay. So then you see that you can actually separate this contribution of these two operators in the limit, because all the operators whose conformal dimension is greater than delta finite can be bounded in this way. So we can consider operator product expansion within the right operators. And if you have this, then if you, for example, consider acting this derivative operator and then using this relation and then takes the limit when delta goes to 0, you get a linear relation among J's. And if you also take a derivative, product of derivative acting on both sides and use this, you can find a quadratic relation between them. Since there is a linear relation between them, you can consider finding the orthogonal basis for this linear operator, and let's call that as J mu. Thank you. And then, since you have quadratic relation, the only consistent form of this quadratic relation is like that. Now, if you assume unitarity of conformal field theory, and if you normalize J to be like Kronecker delta, then you have to conclude that by consistency of the algebra, F mu nu rho has to be the structure constant of either 0, if F is either 0, or the structure constant of compact semi-simple Lie algebra. But you can show that if it is actually a structure constant of compact semi-simple Lie algebra, it contradicts with the assumption that the spectrum goes to 0, because their charges are quantized. So therefore, the vanishing of a spectral gap in the limit requires that F vanishes in the limit. So therefore, we can show that in the limit, you have this algebra of free operators. In fact, you can Bosonize them. And since the derivative of O is like exponential of J, you can show that O is the vertex operator. And you can show that P mu becomes continuous in the limit of T goes to infinity. So this shows that the conformal field theory in the limit is a product of sigma model with target space decompactified to Rn, times compact CFT. Now, since assuming that total conformal dimension is C, then since compact CFT part should also have non-negative conformal dimension, so N has to be bounded by C. Now, you can show that if you the CFT decompactify to N Rn, then alpha becomes actually 1 over square root of M. So from that, we can see that alpha is bounded below by 1 over square root of C. So this is what we showed, that the delta can vanish only in finite distance limit in the conformal manifold, and where the gap decays exponentially like that, and this is bounded by in this way. Now, in the case of superconformal symmetry, we can strengthen this a little bit, because now this C is replaced by C hat. We can show that C is replaced by C hat. And this explains why quintic had alpha equals C equals 1 over 6, because the C hat is 6 in the quintic case, and so this quintic case hits a lower bound. Now, it's interesting to interpret this in the language of AdS theory, what it means. So we need to translate this alpha into AdS parameter. And so I was just talking to Juan before the talk, and so we had some discussion of the scaling. But I believe that this translates into the following statement, that so T here is this a conformal manifold coordinate, so it's dimensionless. But in AdS, the corresponding scalar field has a dimension of square root of mass. So that means that alpha has to have a dimension of square root of length. So in AdS, so therefore the bound translates into AdS radius. Oh, it's the other way around. Planck radius and AdS radius. But I'm just writing this on the board, and I'm going to quickly erase it because I need to check this carefully after the talk. Thank you. So thank you for indulging me with this speculation. So the future program. So there are many things I want to do. I guess one of you, maybe Jake, asked me about converse, and converse is very important. That the spectrum gap always vanishes in infinity distance limit. And so this is something I would like to investigate. And we have some idea about how to do that. Deriving such a bound for in higher dimensions is also very interesting. I think what we are trying to do is to use similar kind of crossing symmetry in higher dimensions. But technically it's much more difficult because you have to disentangle various issues with spins. Now, this distance conjecture, and in particular property of this moduli space of conformal manifold, it's very closely related to the splittability of -1 form symmetry, because basically what we are doing is gauging the -1 form global symmetry on the manifold. And so therefore, in that sense, it's actually related to the weak gravity conjecture, and so the relation to weak gravity conjecture is interesting. Of course, eventually we want to extend it to flat space and digital space or some accelerating universe. And so flat space, maybe there is a tool, because we can consider S-mass-3 bootstrap or some soft theorem for scalar moduli that potentially can be used to derive similar theorems. Anyway, so what I aim at doing to give a sharp boundary between the swampland and the landscape, and I hope that we can sharpen this further. Thank you.
Thank you, Hiroshi. Questions? Yeah, Sohar.
Does it follow from what you said that the volume of the conformal manifold is finite?
Good question. I do not know. Why you think so? Yeah, so we did conjecture that in my paper with Cameron, if I remember it correctly. But I think you know that. So if we understand how this, yeah, I think you probably you might be right. You might be right because we know from theorem 3 that we know exactly how the we can approach infinite. So the theorem 3 says that this is the only way we can approach the infinite distance, and then there the volume doesn't diverge. Indeed, you are quite right. So I suspect, I need to think, but I suspect you are quite right that we can also prove that volume is finite. Thank you.
Thanks.
No, actually, not quite. Because what we proved is that if the delta vanishes, then the distance to that point is infinite. But we didn't say that all the infinite distance points are like that. I think in order to prove what you said, I think we need to show that all infinite distance points are like that. Do you agree? Yes. So therefore, if we can prove this converse, then it follows that the volume is finite. Do you agree? Yes. Thank you.
We know lots of interesting examples where the gap in the conformal dimension doesn't go to 0, but the twist gap, like a small string tension, goes to 0. Do you think your ideas can be adapted to tell us anything about that sort of situation?
It's a good, very interesting question. I haven't thought about it, but at least in conifold case, the continuous spectrum to finite gap doesn't give you this kind of singularity. So I don't know. I need to think about this. Thank you. Juan had some question.
So in the example where you were finding alpha equals 1 over square root of 6, can there be towers that are lighter than this?
No.
Oh, okay.
Near conifold, I know exactly the spectrum. There's a vacuum.
My question might be related to the previous one, but let me ask it again. So in the bulk, these limits where things become light are either the compactification limits or limits where the string tension becomes small, right? But
right.
They don't seem to correspond to theories that on the boundary are free. So this would be...
Yes, so this is a very interesting point. So there seems to be quite a contrast between higher dimensional case and the two-dimensional CFT that we discussed here. So there is actually a very beautiful work by Wolfgang Lershev, who might be here, and Timo Weingart and Lee, that they looked at the variety of Calabi-Yau compactification and conjectures that all infinite distance points are either decompactification or the tensionless string limit. In higher dimension, all cases, at least the case that Calderon, Infante, and Baum looked at, seems to have tensionless string, if I understand it correctly. But this seems to be very different. And so it seems like there is quite a difference between higher dimensional case and the two-dimensional case in that regard.
Well, there are no more questions, then let's thank Hiroshi again.